All right, let's get started. So last lecture, usually I would spend the last lecture, talking like at a very high level, talking about the stuff we haven't covered in this class, because obviously we only scratched the surface of machine learning and sort of high level statistics. But sort of, for the sake of homeworks, I will spend a considerable portion, possibly all of it, talking about backpropagation, which is also fundamental to understanding neural networks and whatever. So I might go over time because I do still want to leave with end with some concluding remarks, because I think there's a lot of interesting things that we haven't talked about and a lot of open problems for people who are interested in doing research, but also just to synthesize what we've sort of been covering in class. Okay, so I guess, yeah, so what did we leave off last time? Last lecture, I sort of gave an introduction to neural networks, talked about the history, why we call them neural networks. The idea is that, we're trying to model a neuron, basically to model sort of the way the brain works. Obviously, this model is very simple. Turns out it works pretty well in practice. We talked about the architecture and the activation functions. And the thing I glossed over was, okay, so we have this model itself. The question is, how do you actually fit the model? And I was like, okay, let's just do SGD, right? So at some level, that's really all we're doing, right? All we're doing is SGD. Turns out that SGD in this context can be a little bit more complicated because there's so many parameters. And so, you might try to be a little bit clever about how you end up doing your SGD. Okay, so I think we're going to start by basically giving you just some intuition. I love to use the word intuition about backprop. Okay, so Probably by now you've seen the word backprop. And I'm gonna give you basically some intuition before we then jump into sort of the nitty-gritty of how to apply backprop to the kinds of stuff we need for the homework. Okay. So we're going to start with a very simple setting, right? So suppose you have instead something silly like fxy is x plus y times z, right? And we're interested in the gradient of f, which sort of in some sense is df dx df dy df dz. Okay, so clearly you could just calculate this yourself, right? So here my df by dx, well, I know that's just z, and I'm done, right? But we're not going to do that. We're going to take it step by step. So what we're going to do is we're going to introduce intermediate values. And right now, it might not be clear why we would want to do this. But for instance, whenever I write these neural networks, sort of the equations that sort of govern the model, I try to be, in some sense, you could write them as just like one really, really big equation, right? Nested. But, for actual like display purposes, it's just much nicer to display them at like multiple equations that are nested. But it actually helps, and it's related to when you actually do backprop. Okay, so what are we trying to do? We're trying to basically calculate the gradients of f, right? Ostensibly, why do we calculate the gradients? Because we want to maximize this function as a function of the parameters x, y, z, right? So what we're going to do is going to introduce this intermediate value. What are we introducing? We're obviously going to be doing it here. Oops. Right? I'm going to define q equals to x plus y, so that then I can just say, okay, f is now q times z. Okay. And it might seem weird to do that, but you're sort of breaking down this function f into as simple a combination of functions as possible. So in this particular case, now each function is either just like a multiplication or summation, right? So then what we can do, this is pretty straightforward, right? And I can basically simply use the chain rule, right? And I have q, right? And I would multiply it by q by dx. Okay, and clearly I'm gonna get the same result. So here, what we would have z times 1. Well, yeah. So I get back z as, thankfully, we know that it should be, if I take the differentiation with respect to x, then I should get back z. Okay, so it seems like I haven't done anything, but let's actually try and draw this graph. So it's basically known as like a computation graph. And let's just go through the motions here, and let's see if something interesting comes out. Okay. So really what we have is, in some sense, we have this computation. And let us suppose that x starts off as -2, y starts off as 5, and z starts off as -4. Okay, so we know that q is just x plus y, so that equals to 3. We know that f is q times z, so it's -12. Okay, so this is sort of basically saying what are the computations required to calculate f? There's some like computer science type things you could be thinking about here. But basically, we're trying to simplify this as much as possible so that each sort of, each composition of functions, each function like q equals x plus y is the simplest operation. Okay. So then what I'm going to do is I'm going to basically calculate the gradients with respect to the things that we see here, right? So here what we have is this would be df by dq, right? And we know that's z, right? And we know that's -4. Okay, so I'm just going to write -4 here to denote the partial of f with respect to q. Okay, the same way here, df by dz, well, that is just going to be x plus y. Sorry, well, just q. I can just write that as q. It's going to be 3. Oh, -3. 3. Sorry, yes. Okay, right. So usually I would write this here as 3. And then if you keep going, you can write your df by dx as -1 and -1. Sorry, -4 and -4. Okay. Okay. So far so good. No questions, right? It should be pretty straightforward. The thing that we're trying to think about is, okay, so remember what we're trying to do, we're calculating the gradients for the purposes of, in this particular case, let's say we want to maximize f, right? So the question is, what do we need to do to the inputs to maximize f? And, basically what we're looking at here is sort of the way that the gradients give you, so the gradients back propagate information about the direction you want to move your parameters. Okay, so let's look at, okay, so we have f here is -12, right? I want to increase it. Okay, so what does that mean? If f is -12, if I have z, I want to increase or decrease? I want to be decreasing z, right? Sorry, I want to be increasing z, right? So the z here, basically, if I make this, let's say a -2, then it's going to be a -6, so this is going to be increasing, right? So how do I know that? I mean, you can sort of like figure it out just by like thinking about what happens, but you can actually just figure that out from the gradients themselves. The gradient tells you essentially which direction you want to be moving your parameters, right? So in this case, 3 is a positive number, so that tells me that I want to be moving my z in a positive way, right? So let's think about q. Q here, actually, I want to be, because the gradient is negative, that's actually telling me that I want to be decreasing the size of my q to be increasing my final function, my final value here, which is f, right? Again, let's see, if 3 here becomes 2, then this would be 2 times -8 would be -8. Sorry, 2 times -4 would be 8 -8, and so this would be increasing as well, right? So here we're basically seeing that the gradients basically tell you, as expected, they tell you, in which direction you want to be moving, such that you're going to be increasing your f. Oh, yes.
I was wondering, so where did you use the table term nada? Because we have df dq, and then we should have dq dx to get df dx, right? But you just did -4 -4. So I guess that would
Yeah, sorry, yeah, because the QDX is just 1 anyway.
oh, right. That makes sense.
Sorry, yeah. Right. So yeah, so it's just 1, so that's why it just is the same thing. I should have been clear about that. So the key thing here is that yeah, so if we just, okay, I can't actually like hide stuff, but if we're just looking at sort of this graph on its own, it sort of makes sense, you can go through the motions. If we were just looking at sort of this graph on its own, right? So if this was like x and y and I had a q, and that would be x plus y, right? Then I would want to be increasing both of these values to make this value bigger. But the point is that obviously this thing has to be decreasing for this to be bigger. And so this is nice because the gradients basically tell sort of, this is where the the back propagation, the word comes in. The gradients back propagate back to your original parameters and actually tell you that, okay, if I want to be increasing this final thing f, I actually need to be decreasing the x here, because a decreasing of this x will then decrease the q, which will then decrease the f. So, in a very heuristic-y type of manner, what we're trying to look at here is the backpropagation is, okay, for one thing, what it is just chain rule, right? You're sort of doing some dynamic programming in the sense of like you want to basically represent every derivative with respect to your final, with respect to the parameters that you care about in terms of like intermediate values, right? But the other thing that's somewhat useful is that you're sort of thinking of this as like a signal that's being passed back about which direction to move. And so this is actually why yesterday we talked about, when we talked about like the activation functions, like just all the activation functions where you basically have, either gradient of 0 or gradient close to 0, right? So remember, let's see, so like ReLU negative domain, the derivative was equal to 0, right? So if the derivative of that is going to be equal to 0, then what happens is, this red number here is going to be 0, right? And then everything, to the left of this graph is also going to be 0. So that's basically, you're not moving it in any way, right? And you think about it, it's because, because you're at a flat place, you don't know where to go, right? You don't know where to go to make this function better or worse because you're at a flat place. That's what gradient 0 means, right? And so it's fairly important that you don't want to have these situations where you're just, a lot of your functions, a lot of your intermediate values have a gradient of 0, because then it's just basically going to kill off that whole section of the network, right? Does that make sense, right? So the, in one way, backpropagation is really just calculating derivatives, and it can get pretty messy, as as you probably figured out in the homeworks. But at an intuitive sense, you really should be thinking of this as just like some way of sending a signal back to tell where the parameters should be moving in order to be increasing or decreasing your loss function, or the final product that you care about. In this case, it's f, but usually it's some loss function. Okay. So that should be the intuition. Any questions? Okay, so I figure that's pretty straightforward. We're talking about a very simple function here, right? We're talking about this. This is embarrassingly easy. So let's go to proper example, right? So, look at a proper example, which we're going to call logistic regression. Sort of. Right. So this should be familiar. What we have is we have these 2 points. X is in R2, F is in R3. Right. And I'm going to, define my loss function as L is sum 1 over n, I from 1 to n of Li, where Li is probability of y equals to yi given xi. Sorry, that is not what it is. That's the unlogged version of it. Okay, and so this should be like familiar to you at this point because we've talked about this many times. But let's just digress for like a hot second, right? Remember, we have maximum likelihood. I'm sorry. Suppose we're thinking about likelihood, right? Then what we would have is we would have products from 1 to I to n of probability of yi given xi. Right? I mean, this is literally sort of the definition of likelihood. Right. So I'm saying, suppose I see x's and y pairs. Sorry, not pairs. Data xy pairs from 1 to n. What is my maximum likelihood? It's literally just that, right? So I want to calculate the likelihood of seeing that given my x, right? So that's just by definition. Then what I do is I just do, minimum log likelihood is then just going to be minus sum from 1 to n of log py equals to I given xi. And voila, that's what you get. Okay. So that was a sidebar. Let's go back to what we're trying to do. So let's remember what the setup for this is, right? What we have is we have f is x, w x plus b, right? And p is softmax of y, of f. Okay. So then if we're just reading it off, then really what is this p of y equals to y given xi? Well, that's just p of yi, right? Because how do we set up this model? We're saying, first of all, you take this linear combination of x, and you apply softmax, and then the index. Okay, well, so let's be a little bit clearer, right? Probably y equals to k given xi is really pk. That's the way we've sort of defined this, right? P is a vector in R3, right? That corresponds to the assignment of the probabilities that we attach to that particular class. Therefore, P of y equals to yi is really just P of yi. Okay. So let us keep going. So really, what are we doing? So the goal, let me write it here. Goal is to calculate Li over W, dLi over dB. right? These are the two parameters that we have, right? We set up a model, we have a loss function, and we're going to basically try and optimize the log structure with respect to the parameters, right? These are the parameters that we can tune. They are basically what constitutes the neural network. And so we're just going to calculate the derivatives with respect to these two parameters. Okay, so far so good. Any questions? No questions. Cool. Oh, maybe I will have time to talk about the future. Okay, sweet. Okay, so as I said, we're going to do backprop, which is basically saying we're going to just take our time with calculating these derivatives. And so we're going to just basically, do it piecewise. I'm not sure if piecewise is the right word here. So let's just not be ambitious, and let's just start with FK. Okay, so I want to show this first, but I need to actually think a little bit carefully about how to write these things together. Okay, so first of all, as we said already, my Li is minus log of Pyi. Right, so if you remember what P is, that is log of softmax of F of Yi. Right, what is softmax? That's negative log of this ugly function xfy over some x fk for k. Right, what's that? That's negative fyi plus log of some x fk. Okay, so that's just what log of Ly is. Then if we actually take this derivative with respect to fk, which is what we have here, so let me just put this down here now. Right, dli over dfk. Well, how do I take this derivative with respect to this guy here? It's just minus indicative function of yi equals to k plus pk. Oh, pk for those Cantonese speakers. Oh, okay, sorry. Wait, I feel like did I miss something? Oh yeah. Okay, so I just I want to spend just want to make this comment. Just this guy here. For most of you, I hope this is going to be intuitive, but like this really is the intuitive thing, right? Because what is this expression? This is just saying what probability do I assign to the class that I see that's attached to this X, right? And so clearly I want to be maximizing this probability, right? Like I want to assign high probability to those that I see. Okay. So question, K in partial FK not same as summation index. That is correct. Let me change this. Yeah, so I'm gonna call this V, just so no one is confused. I have K in other places too. Scheiße. Okay. Cool. Right. So it is you should be able to see that if I take the derivative of this, I get PK. Sorry, because if I take derivative of something with respect to log, the bottom thing becomes the denominator. The top thing is I differentiate it. Then actually what comes out is just the FV where V is equal to K. So then that actually ends up being just PK. Cool. Okay, so far, I haven't really done much. All I've just looked at is this particular quantity, right? And we see that it looks like this. So far, so good, right? Okay, so then what I, just for notational sanity, I'm going to write this like this. So it looks like P1 minus indicator function of yi equals to 1. P2 minus indicator function yi equals to 2. P3 minus indicator function of yi equals to 3. Okay, so the partial of Li with respect to f, I'm going to define this to be P star. Okay, so it's going to be a vector P star. And here is for your reference to the lines of code. I mean, it's sort of hard for me to sort of go back and forth between lines of code, but basically on my sample code, it's line 57 to line 59. Okay, I mentioned this in Piazza when someone asked about what on earth XY 2pos does. Basically, it's doing this. So you start off with the P matrix, and then you -1 depending on which yi you have. Right? Oh, a question: does the writing also lag a lot for everyone? Oh, sorry. Is it? Okay. Huh. Weird. What to do? Maybe I will hide my face. Oh, 10 seconds, Jesus. Okay. So let me turn off the share first and then turn it back on. Okay. Okay, is it fine so far? I'm starting to scribble. Maybe not. Yes, no. Okay, cool. Oh, whoa. Okay, cool. So unfortunately you can't see my face. Probably that's a positive. All right, so okay, so let's figure out what we're doing here. Okay, so what we have is we have our Li. Okay, just to back up a little bit, what I do Li here is because I care about just one data point at a time. So this is just one data point, right? So this is one data point parameterized by I. Okay. So what am I doing here is I'm just looking at this one loss with respect to one data point, and I'm taking the derivatives with respect to f. And so here I'm going to write this as P star, which is just basically the P vector with this weird minus thing. Okay, and if you look at the sample code, it corresponds to line 57 to 59. Okay, so far this is pretty standard. There's nothing too complicated about this. Yeah, okay, so let's move on. Also, yeah, if there are any questions, please stop me. So let's go to the next level, right? So what we care about is df by dw. But I'm gonna, be trying to interpret the line of the code. Okay, so I wrote this. I wrote this up in Piazza. I hope you have access to Piazza. For those of you who don't, what this is basically saying is, I start with my p vector, and then I'm just going to -1 for, I'm going to find the yi's, and then a -1 in the relative place. Yeah, so suppose yi here was equal to 2, then I would have this p vector and I'd -1 at position 2. And so you should try and figure out how that works in the code. Not too important right now. There are much more important things to know later on. Okay, so let's just work through this, and if I have time, I'll go back to that line of code. Okay, so let's, as I said in the homework, I think it helps to just sometimes work with like the individual coordinates. Okay, so first of all, it helps to know what fk is. Fk, remember, was w, so f is wx plus b, so I can actually write fk as wk times x plus bk, right? So here the k corresponds to the particular row, and so f is as such, right? So in particular then, I'm going to write this a little bit to the right here. So then fk over wkj, well, what's that? That's just going to be, okay, so let me just write it out like this, plus bk over dwkj. It's not surprising that this is just going to be xj. Okay. It's also not surprising that if I do fk over bk, I'm going to get back 1. Okay, so here I can be a little bit clever and say fk over dwk is x. Okay, yeah, I may or may not use this later, but it's not so far. Yeah, so far I haven't really done much. I might not use this for now, but later on I would use it. So this is not, this is fine, but what I want is I want the full chain, right? So I want the derivative of Li with respect to wkj, right? Well, that's just dLi with respect to fk times dfk with respect to wkj. What did I have for the dLi fk? That was just p star of k, and then I multiply by x of j. Okay, so anyone have a question? There should be something maybe a little weird, maybe, or not.
What happened to the indicator y equals thing? Did that go away?
Oh, so I put it in the p star.
Oh, it's in the p star now. Got it.
Yeah. Sorry, I cheated. Yes. So yes. Sorry, which is why I write p star. Yeah. So that's a separate thing. The p star thing is here. Here you have to be a little bit. Well, actually, this part is fine. Sorry. Okay. This part here is fine.
So I guess I'm just wondering, because when I read a bit online about derivatives of softmax and stuff, there were usually 2 where you had to consider if I equals j or if I doesn't equal j. I'm not sure
I
why.
equals j. So I think you're, well, first of all, it just depends on what I and j are in your setting. I have, sorry.
Or maybe it's because we're just taking the derivative of fk and not the whole matrix or something.
I want to say that it's all about this guy here. So they're just like, there are a few ways you can think about this. One way is to define fk depending on, what, if k equals to whatever. The other way is just to do it like this. Yeah, I feel like that's probably what it is. I mean, this is correct. So whatever they do on the internet eventually should be this. They just might write it in a different way. But at least for the code that we set up, it is like this. So I think it's probably easier to think of it like this. Yeah. So, I guess we can sort of, I guess I might have gone a little bit quickly here. Right, all I'm doing is I've defined my, I know how this is written. I've expressed it in this form, and I've calculated the derivatives. And so this is, this is just a concatenation of these derivatives with respect to different k. So I have, k from 1 to 3. And so I basically put them just into one vector just for convenience sake. And I'm just using the chain rule here to multiply these two out. And basically that's what we get. Someone says, I think the difference is whether you split up log of softmax you did here, or if you do 1/p times d softmax p over dp. Oh, okay. Yeah, okay, yeah, that could be it. Sorry, yeah. So I'm being a little bit, I wouldn't say I'm being a little bit lazy because we actually don't care about these intermediate functions, but I think what's happening is if you actually do this like dli over dp and then times dp over df, but it doesn't really, you don't really need to do that. It's just easy to go straight. So the eventual function should be the same anyway. Okay, so let's accumulate all this together. So what we have is we have d of li dw, right? That's going to be p star x. Okay, so let's see. If I write this as a 3/1 and I write x as a 1/2, so I guess this should probably be a transpose. Then what we have is this is then going to be a R3/2, right? And W is indeed a 3/2 matrix. Okay. Any questions so far? Should be fine. Okay, so this is not exactly what we have in the code. And this is where we get to the computational trick. And why we have a computational trick is because this is only for a single I, right? So in the computational trick, what we do is basically, well, we notice that, well, L is the sum of Li. Well, okay, forget about the 1 on n here. You can do that whenever you want. So really, that's sum of Li, that's sum of, sorry, what am I writing? D of dw is sum of dli over dw. Right, so it's the sum of all these things. So what you really want is you can then write this as like capital P star x transpose, which is then going to be a 3/n and an n/2. And nicely, this still gets you our 3/2. Okay, so what did I do? This is sort of I mean, this is basically like how you make sure everything is still like nice matrix operations. Essentially, if I forget about this green part, I'm calculating my gradients with respect to one particular data point. And the way I do that is I just, I calculate the P star and I have X transpose and I take the matrix multiplication of these two and I get back a matrix and that gives me the derivatives, okay? But clearly this is just one data point, right? I have n data points. So I can just keep doing this, right? So if I were to do this across all of them, right? If I were to take a sum, it should be, I mean, okay, so it may not be that obvious that the way you can tell that it works out is because if I put an n here and I put an n here, these two n's cancel out. And so really what you're getting is a 3 by n and n by 2, then these cancel out. So it's basically equivalent to taking the sum over the I here. So as a result, you actually are just doing matrix multiplication when in fact, you're doing this across all data points, right? And so this actually corresponds to line 62, okay? So that's the line 62 where we just basically multiplied P star by X. Maybe I did the different way around, but ultimately you need the ends in the middle and so they can cancel out so that you get 3 by 2. But as I said in the office hours, this is basically a computational trick, right? You could conceivably do this for every single data point and just sum them up and you'd be fine. But this is obviously much nicer to do this way because you don't have to, keep track of what's going on. Okay. Any questions? Cool. Okay, easy. Easy peasy. Huh. All right, so let us go to the next step, right? So what if we added another layer? Right, so here we're just gonna basically, it's a little bit like starting off with the previous one, but now instead of my X being here, this is gonna be my H, my F is still the same, and my X is gonna be here, right? So I've just basically added a new layer, blah, 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 so on and so forth. Okay. Then here I have, I'm gonna write W1, B1, W2, B2, right? Because now I have two weights. Okay, so what is the expressions that I'm dealing with here? P is always soft max of F. F is the same thing as we had before, but now it's H plus B2. H is a little bit weird because now I do ReLU of Z, and Z is W1X plus B1. Okay. And it probably is going to help to have some of these coordinates. W2, I'm going to write this as R of K times H. Remember, K is 3. B2 is R of K. W1 is in H times D. B1 is in R of H. Equals to 2. Okay, so straightforward. Everything's good. Okay. So, sort of want to move this here a bit. Okay. So the nice thing about doing all this is that basically a lot of the calculations are basically the same, right? Because you're just adding layers onto each other and we're being general about the form of the layer, then a lot of it is just the same as what we had before. Okay, so especially this first part, the loss function is going to be the same. So what am I going to do? For my first layer, so like for my second layer, the DLIs with respect to the DW2s and DLI with respect to DB2s are the same, right? So because there's no intermediate layer, I don't need to worry about them, right? So what are they? They are the thing we had before. Okay, so now we just need to keep going. So where it starts to be a little bit different is the fact that now I need to take the derivative of f with respect to h, right? Because I want to pass through h to then get to x, right? Well, not x, to w1 and b1. Okay, so what is df over dh? I want to do this in terms of k and j. Okay, so here I have d of wk2h plus b2k over dhj. Well, that's just going to be w2kj. All right. Then as I go through my dh over dz, well, that's just indicator of zj greater than 0. Okay. And really, actually, these are just the only two new things, right? Everything else is actually the same, right? So this guy's new and this guy's new. Because once I'm at the z, I have dzj, right? If I do this dw1, well, again, this is the same thing as what we had before. Right, so like just adding one layer here, the only thing I add is basically these two sort of partials, okay? And then everything else is the same. The question then is, okay, how do I sort of aggregate all this information up together to actually take the derivative with respect to my loss function? Okay, so any questions? This is all good so far? Oh, I don't need to, you guys can't even see me, so. Cool, okay. No questions. Everyone's still here? Just check. Oh, cool. Okay, still people are participating. Okay, so let's take a go at putting this all together in one way. Well, actually, okay, so we actually need to do it with respect to hj first. It's sort of important, right? So dli over partial hj. What is this? This is going to be dli over dfk times dfk over dhj. Okay. But now k is free. And so if k is free, I need to sum over them. Oh, there's a question. When we compute dfk over dhj, do we not have to account for the ReLU in the definition of h? So I've split it up. Where did I split it up? Here I cheated it. I cheated a little bit. So it's a little bit different from the assignment. I write z here, so I actually make it sort of two passes. So the h here doesn't matter anymore. And then once I do the h to z, then I have to take into account the ReLU. Yeah, sorry. It's actually not particularly necessary to do that, but it's sort of, I think it's a little bit cleaner because yeah. Okay, so this thing here is very important. Throughout all the stuff I've been doing so far, there haven't been free parameters, right? So if, if I look at this guy here, there's a kj here. The k, is fixed because that's where the k is, and the j is free, so that's fine. But in this particular case, I have an I and I have a j. Well, sorry, I don't have I because I is just a data point. The only thing here that's fixed is a j, but then k can vary. So as a result, you need to actually sum over all the k's, right? So basically what we have is sum over k, and we know these individual components. What are they? They are like p star of k times, is this w2kg, right? Okay. So really what this is this is W2 transpose J times P star. Or another way to say this is DLI over DH is W2 transpose P star. And, as someone was saying in office hours, you just like check by looking at the dimensions of these things. What is W2? W2 was K by H. So this is H by K. P is K by 1. And voila, we have H by 1. Okay. I mean, I could keep going. Although, like, as I'm doing this more and more, I'm like, am I just giving you guys the solutions, which I hate doing, as people in my office hours know, and people complain to other TAs about. Anyway, it's fine. It's the last day of class. Okay, so what we have is finally DLI over DWJK. How are we going to do this? So we have DLI over DL. I don't want to put the K here. We could actually use the K down here. FK, sum over K times delta FK over delta HJ times delta HJ over delta W. Sorry, this is L, JL. Oops, I missed one. Sorry. There should be a Z. ZJ times delta ZJ over delta WJL. Our statistics grad students are very funny. Sorry. So our grad student said, well, I guess everyone can read. So yeah. So well, for the people who are on YouTube or watching this in the future, they said that there's a lambda term, so it's actually not the true solution. Not the whole solution. No, obviously not the true solution. Okay, so funny, good stuff. Okay, so yeah, we're almost there. Yeah, some people were saying like they took like days with this. Well, obviously in hindsight, everything is easier. Okay, let's take a look at what this ugly ass expression is. P star K, this is W2 of K, this is indicator of ZJ greater than 0. This is X, nope, I forget what this is. This is, oh yeah, it is XL. Okay. So the first part, we've already actually like figured this out. This is actually W2J, oh, sorry, W2 transpose J, right? Times indicator of Zj greater than 0 times XL. Okay, so if you look at it, this part is the J part, this part is the L part, right? So if you squint your eyes a little bit, you can see maybe that what you have is you have something that looks like this. Oh, I missed a P star somewhere. My bad. Yeah, how do I do this? I'm gonna get rid of that. Let me move this guy. There should be a P star here, and then times XL. Okay. This is J, this is L. Okay, so really what we're doing here is this is P star. And I'm gonna write something that looks a bit weird in a Hadamard product Z plus. And then multiply that by X. Okay, so, oh, wait. Z plus actually is just the positive part of Z, so this is not that nice. I shouldn't write it as Z plus. That would be confusing. So I'm still going to write this as Z greater than 0. X. Okay, so this is basically saying I have okay, this is sort of not particularly nice. This is a, okay, I'm just gonna write down what the actual things here are. Right, this is, we had before, this is H by K, this is a K by 1, right? And then this is going to be X transpose. So this is a 1, whoops, 1 by D. Right. And then here, I'm writing this. This is also a H by 1. This is the Hadamard product. So basically, I'm saying if I have two vectors here, I just basically do pointwise multiplication for each entry. So I get back an H by 1. Okay. So after all that, it's an H by 1 by 1 by D, which is a H by D. And, oh, this should be W2. I missed the 2. Missed the 2. Okay. Oh, this should be a 1. Sorry, I missed the 1. What am I doing? This is a 1. This here is a 1. Okay. And H by D should be the dimensions of W1. Very nice. Okay. So, sorry, that was a lot of calculations. No one has interrupted me, so I assume everything is good. Oh, why is the element-wise product not stuck to the right of W2, or why can we commute it? So, I mean, this is just an ugly way of writing this. I'm just saying, essentially what we have is we have this is a vector, this is a vector of length h. And then what I'm going to do is I'm basically zero out, you know, the z's where it's greater than 0. So that's just really what it is, right? So basically I have two vectors, and I'm going to basically the one on the right, well, you can't see my hand signals. This vector on the right is just a vector of 1s and 0s, And then I just basically do how to my product between these two vectors. You can do it. I mean, it's just, I'm not sure what, it's the same thing. I'm not sure what you mean. Oh, sorry, you're saying, why is it not stuck to the right of W2? But so this guy is here, so I'm not sure why this should be here. You're saying this should be in between the P star and the W2? Okay, I'm confused. Okay, I mean, so right now this is where it should be, because it like this guy corresponds to this. I guess we can draw arrows here, right? This corresponds to this, to this. So everything lines up. Everything seems to work out well. So then what you notice is that you have the same thing as before, right? Because you have these ones here. Oop, I don't want this color. We have these ones here, and that's exactly where you put the ends, right? So you want to make sure you put the ends in the right place, because the end card comes from the X's and it comes from the P stars, right? So in the same way, if you set this up, then actually this is going to be an N and an N, but then the N's cancel out, and so you don't actually have to take each individual loss with respect to W1. You can just take the sum over all of them. Okay. So that is the answer to problem 1, essentially. Any questions? Okay. Cool. No questions. So let's see. All right, so then I guess we will talk about the last like 10 seconds. Sort of talk a little bit about state of machine learning. Okay, yeah, no, please, if no one has any questions, I'm going to move on. Otherwise, please stop me. I mean, if you guys have no questions, that's perfectly fine. It's just surprising. Okay, so this is going to be somewhat short. Oh, is there a difference between backprop and reverse mode auto differentiation? So I'm not that familiar with reverse mode auto differentiation. I remember seeing an article about it. My feeling with that is that it's just it's like a CS way of sort of solving this problem. I don't actually know the difference. I ultimately in both cases, like what you're doing is you're calculating gradients. I think the reverse mode auto differentiation is a way so that you can actually do this in a principled manner. Like if I give you, if I give you one function, then you don't need to have to, be able to calculate gradients. You can just do it in do it automatically. So I think that's what it is. I'm not too familiar with that. But in terms of like actual implementation, that's where it differs. But backprop, these are the same things. It's like they're basically doing backpropagation. You're basically calculating gradients. How do you calculate them? You can do them manually, or you can do them in some more intelligent manner. Yeah, actually, so sort of hopping on that. what you like, part of the reason why, for instance, like neural networks, a lot of the packages, with these like deep learning, all these types of packages, they're all in CS now. The reason why they're in CS is not because like we statisticians don't care about them. It's because these have turned into essentially like really complicated computer programs that require a lot of efficiencies and like computational tricks. So it's actually a lot of like computer engineering. A lot of these people who end up doing machine learning, half the jobs in machine learning are machine learning engineers. Someone needs to be actually coding these things up, and my feeling for what actually goes on in industry is that most of the time is just spent trying to code up something, make something faster, or add to some architecture by basically improving on the code on like the base libraries that you have. And so it's very different from statistics types of research, where I think we're from a much more mathematical place, where you have some theory, you want to prove something about what you're proposing. I find that machine learning research more and more so is I'm not sure if it's engineering, but it's basically like, yeah, you try a bunch of things, you have some intuition, maybe, you can always come up with some intuition that sort of backs up what you're proposing, and then really you just see if it works, and if it works, if it beats the side of the art, then you have a paper. It's much less principled than like statistical research. So actually, yes, that's sort of what I was going to talk about here. So I was going to essentially talk about the differences between statistics and machine learning. And so there's like certain things about them that are subtle, but at a really high level, what the difference is statistics cares about inference and machine learning cares about prediction. So what does that mean? What that means is, in terms of statistics, what I care about are things like p-values, hypothesis tests, central limit theorems, stuff like that. And then in machine learning, again, I just care about prediction, right? I just care about how well I do on holdout data, right? So another way to think about this is like, basically in statistics, sort of parameter is king. I cannot write things too quickly. Whereas in machine learning, essentially, prediction is king. And how that's actually borne out is, I think, actually pretty interesting. I'm not sure if I think people have obviously thought about this, but I think there's a paper in here somewhere, which is this idea that if you think about in statistics, what we like is we like functions that look like this. So this would be like, like your likelihood function. And the reason why you like functions that look like this is because what you care about is you care about your parameter, like, suppose this is your true parameter theta star, right? And so if you have a, I have some sample of my likelihood and it, looks a little bit weird, because it's sort of peaky, what that means is that my theta star, like my theta hat, right, is not going to be moving too much, right? So it's, it could be down here, but it's still close to my theta star, right? And because the point is, with statistics, what I care about is my true parameter. So I assume that there's some true parameter, and so I want to know how far away theta hat is to my true parameter theta star, right? So what I care about is basically this distance, and I want to minimize this distance, right? And on the other hand, machine learning, what I actually like is I like the opposite type of likelihood, right? Why? Suppose this is, in some sense, like, like the actual best theta, right? If I have a flat likelihood, or if I have a flat loss function, then, if my thing moves around a little bit and my maximum is here, well, it doesn't matter because even though, okay, let's make this a little bit more extreme, right? So if it looks like this, right, then my maximum, let's say, is around here. So now this guy is a little bit further away, but I don't really care because all I care about is prediction, right? I want it such that this the distance between these two things are minimized, right? Okay, so is this clear? I haven't put any axes. Right, so you can think of this as like the likelihood function. And so, this is the likelihood, and this is like my theta, right? Here, you should think of it as like the loss. So think of it as like the loss. Oh my God, what am I doing? As the loss function. So L, and again, this is like my theta. So this is like a one-dimensional version, but it's not. You can extend this to high dimensions. But like one of the heuristics that people talk about when you look at neural networks is that the reason why neural networks work so well in practice is because you set up your landscape in such a way that your minima, right? Obviously, you're trying to minimize these loss functions. The minimas actually happen in like a flat area, right? So you have this flat areas. As a result, you're basically going to get really even though your actual thetas, your parameters themselves, could be very far away from the global minima. The predictions are still good enough, right? Whereas that's really not what you want when you're looking at the likelihood, right? You believe that there's some true theta star, and so you don't want to be moving really, really far away. You want to be as close as possible. And so what you care about is these peaky loss functions or peaky likelihood functions. And I think actually, okay, so this is like, turning into exposition and sort of maybe over the heads of a bunch of these, a bunch of you guys. But, I just wanted to bring this up. I think actually this is sort of handicap statistics because in reality, what we know is that most of the time there is no such thing as a true parameter, right? There's no such thing as a true parameter theta star. And so when you have noisy data or when you have certain under certain regimes, when your data is very, very complicated, you actually do prefer this type of model that prefers this type of curvature for your loss functions. And so this is why I think machine learning is doing a much better job in sort of these state-of-the-art methods, and why statistics is sort of lagging behind, and why we as statisticians need to sort of think about how we can merge the two, sort of take inspiration from machine learning. Interestingly, I think there's also this other duality going on, which is that, if you think about what's also happening is I think basically these two fields are sort of merging together. I do statistics and machine learning, and one way they sort of they combine is this notion of interpretable machine learning, right? So I think I've said this before. If you think about neural networks, right? So if I compare the two extremes, I compare a linear model to a neural network. A linear model is like super nice. It's super simple. I can look at the parameters and I understand what they mean. They might not be great for fitting the model, but whatever. Like I have really nice interpretability. Whereas if I look at the neural network, I mean, we haven't even talked about this, but like if you think about the parameters, like these W's, these B's that we're actually optimizing for, they're almost meaningless, right? Obviously, people are trying to come up with nice things that you can then interpret. Like if you looked at the LSTMs, we had some ways to try and interpret what each sort of hidden unit was doing. But this is sort of an ongoing project, which is that like we have these machine learning methods, and they're basically, they're known as a black box, right? But in certain settings, we don't want that, right? So essentially what this is, we basically want to have our cake and eat it too, right? We want machine learning, we want things that are really good at predicting, but we also want to be able to interpret, which is essentially saying we want inference, right? We want some parameter that we can then pick and then decide on, and then say, okay, this is what this means. And so to me, it's sort of interesting that like, basically it's a question, it's an open question, like, can you have both sort of, ideas about inference and parameters, as well as sort of ideas about just forgetting about the parameters and focusing on the prediction. And in some sense, it seems like these things are contradictory. But there are steps to basically try and sort of solve this thing. And this is a sort of a new topic called interpretive machine learning, which I've thought about quite a fair bit, but I haven't really done much work on that. So this is sort of a new topic in machine learning. The other thing which unfortunately I haven't had time to mention, which I think is really important, and that's another takeaway from this class, which we don't unfortunately have time to talk about, is basically the idea that these machine learning methods are basically so powerful at this point that you're basically going to pick up on all types of relationships, patterns in your data. And if your data is created by humans, then it's actually going to pick up on all the biases and stereotypes that humans have. And so an open question is like, how do we deal with this, right? Like, if you looked at the word embeddings, that was actually going to be the extra credit homework that I end up never writing, was like looking at word embeddings and how that relates to like gender. And so you can look at examples where the word embeddings are basically they have incorporated the biases of like doctor to man is a doctor as woman is to nurse, for instance, stuff like that. And then there's also a bunch of stuff we haven't covered. A student was asking sort of what would be next for like a nice follow-up to this class. I think right now the departments are sort of changing. The field is also changing so fast that it's hard to say. Our department sometimes has like special classes. This semester we had something on like deep learning with application to bioinformatics or something like that. CS people or like linguistics people have like natural language processing, which I think is a fairly natural extension to this class, a follow-up to this class. Then we have sometimes classes that take on a more theoretical approach to machine learning. I will say though that at least the previous editions of that theoretical class are somewhat dated. Like there's a lot of interesting work now on like the theory of neural networks, and like that's something that I'm working on. Something I hinted a little bit at last lecture when I talked about like the interesting thing about like if you have a linear neural network, this seems really stupid because now all your you don't have any nonlinear activations, and so this would be equivalent to just running like a simple one layer. It turns out that having multiple layers actually does something really interesting there. So I think there are interesting types of classes. I'm not sure if Yale will be offering them, unfortunately. Again, if you're interested in any of these things, I have like a whole list of papers that you could read for the rest of your life, probably. Yeah. So what else? Sorry, that was really, really fast. I hope people. Okay, so yeah, I wish the end of semester was a little bit more normal, but hope everyone is doing well. Feel free to email me. Good luck with the homework, and yeah, thank you.
Until when should we finish the homework now?
I think I said Friday, but yes, it should be Friday. Okay, so someone says, you may choose to do the following problems with respect to just the two-layer network. You will incur penalties of yeah, so yes, you'll be penalized for doing a two-layer. I haven't decided your penalty. I think last semester I said like eight, like you just have a maximum of 80% of your I think it's something like that. So it should be on grade scope. You should be able to tell from the is it called, the rubric, what your penalty will be. Someone else asked what's my main research. Okay, well, everyone else can leave if you have better things to do. So yeah, I actually don't really have a main research. I have a bunch of different things that I'm working on. Most recently, I am working with a student on fairness and machine learning. In particular, I mean, I would have to describe sort of like what's going on. Essentially, it's trying to take into account the fact that, you know, these machine learning models are, you know, put into the wild, and it's going to interact with humans and society, and it's going to create feedback loops. And so then the question is like, how do we sort of take those into account? So it's a little bit like economics, like, you know, you have feedback mechanisms in economics and so on and so forth. So that's one area I think it's important. Interpretability, I have some ideas. I haven't sort of actually sort of written much about that. But I think it's really important, and it should be a big field in the future. The other thing I'm working on is the thing I mentioned about like theoretical neural networks. So yeah, maybe this is better. Like, you know, you can sort of schedule a time with me outside, and I can spend more time sort of talking about it. But essentially, we're looking at so we haven't talked about regularization. So, you know, in the homework, you know, we have this penalty on the size of the weights, and you might ask what types of penalizations, what types of regularizations are helpful in these trainings of the neural networks. And what's been sort of discovered is that actually depth sort of plays an implicit role of regularization in terms of sort of dampening the singular values of the weight matrices. And so there's this interesting idea that, you know, you actually don't really need to do regularization because, you know, depth plus stochastic gradient descent is somehow doing some form of implicit regularization. So I think that's there's just some open questions there. And actually, the other thing I didn't mention, I was supposed to mention this, which is that there's a really interesting phenomenon in machine learning, which is, and I hinted at this when we talked about AdaBoost. If you look at the classical way of thinking about statistics is like this bias variance trade-off, and so, you know, you don't want to overfit. But what you find with these like fancier models, especially with these deep learning models, is that you essentially get best performance, you know, after you've basically fit your data perfectly. So you have training error of 0. So clearly this would be in the overfitting regime, and yet you're still able to basically generalize better than, you know, if you were to sort of do the bias variance trade-off and, like, you know, you have the U-shaped curve and like you fit there where you're like, so it seems like these state-of-the-art models don't actually sort of conform to this intuition that we have about bias variance trade-off. And so there are people trying to come up with like explanations for what's going on. A student and I have some ideas about why this may or may not be the case. So that's, you know, again, an interesting area. What else? Then other stuff that I do, which is not related to machine learning, or stuff like social networks. So I'm in Nicholas Christakis's lab, and we, you know, play around with social networks, play around with sort of like random graph theory. So some theoretical work on that. Yeah, and then there's a bunch of other smaller stuff, which probably shouldn't talk about. Cool. All right. Any other questions?
Professor, can I ask a question about the homework problem 1, a specific aspect of it?
Sure.
So I asked the question about the element-wise product being stuck to the W2. Yep. The only reason I asked this is because, so if you take, I don't know, maybe you could humor me and
sure,
and just like write down the steps, because I don't think I'm interested to see what's going wrong here in the actual mechanics of taking the derivative. So if you just take the derivative of h2 with respect to h1, and you don't explicitly decompose it, the ReLU
Oh,
as a part of
okay.
it, and you should get something that looks like, partial h2 with respect to h1 is equal to the W2 matrix, and then there's some sort of element-wise product or something with an indicator or step function for basically the result of h2 in this case being greater than 0. But it doesn't seem like the dimensionality checks out when you do it like this, and I'm not quite sure. So I don't think it would work unless you rearranged it. So obviously it does work when you rearrange it as you did. But assuming that you're just kind of subsetting to the in this case, when you have these four partials multiplied by each other, if you're just looking at the second and the third being multiplied together, the dimensions I don't think work out. But if you just kind of look at the partial in a vacuum, I don't know. I think it should have to work out. So I'm a bit curious about that.
Huh. So why would this not work?
If you just took the partial of h2 with respect to h1, I think you'd see what I'm saying.
Yeah. Okay. I mean, okay. You can show me your like calculations offline. Like I don't have them in front of me right now, so it's a little bit harder to see. But yeah, I think sometimes this is probably also just the part of the reason why like you want to do it like incrementally as well, just because it's easy to, I don't know, like things become weird when you sort of like take multiple steps. Right now, I'm not sure what the answer there is.
Yeah, I mean, it makes sense that the derivative of, even if you did it kind of coordinate wise, you'd have some derivative, the partial of h2 coordinate h, like uppercase h2, so in some it's a vector with respect to the partial with respect to h1 and some h1 coordinate, capital H1 coordinate within h1, then you get some answer that looks like a W2 element h2 h1, where these are the capital H's that represent the dimensions, basically indexing really explicitly like that. So you get this this element from the W2 matrix, and then you would basically have if h2 was greater than 0, then you would just have that W h1 h2 sub h1 h2, but if not, it would be 0 basically. But when you try to aggregate that within that step alone to a matrix, it looks like the dimensions shouldn't work out because h2 doesn't have the same dimensionality as W2. So doing the element-wise product of them doesn't seem to make sense unless you do like column by column or something, but I'm not quite sure.
Yeah, I mean, yeah, I'm not. Yeah, I for some reason I can't see it. Yeah, you can send again. Just I guess if you send me the stuff, I know it should be pretty clear. It should be pretty obvious. But for some reason, I'm not